if I start off with the stuff that I wanted to cover today, we'll see how do we formulate the hypothesis given a problem statement. We'll see what a null and an alternative hypothesis is. We'll also see type 1 and type 2 errors. Then the concept of confidence intervals. Then we'll see how do we do hypothesis testing, what the different hypothesis tests are. In the hypothesis test, there are one-tailed and two-tailed tests. We'll see that. Then we'll see tests of mean. So there are three types of tests: test of mean, test of proportion, and test of variance. We'll see all of that. And finally, power of test. We'll see if we have time, but personally speaking, power of test is not very frequently used. So if you are okay till the concept of hypothesis testing, that works fine for all of the cases. So we'll see if we can do power of test, but that's not really important if you ask me. So starting from the hypothesis formulation, so I'm considering the case of Coca-Cola manufacturer, which is you can consider it to be close to a real life case study, because this was one of the case studies we had done some time back. So I can't project the actual data here, but I've tried to formulate the problems from there so that you're able to relate how do you imply or how do you use hypothesis testing in your real life problems. So the problem that I have here is, so the 600 ml Coca-Cola bottle that you get in the shops. So there, if you see the volume that is mentioned to be 600 ml. Now, how do you know that that volume is 600 ml? None of us have measured it. We say that it is a 600 ml bottle and we pay the price for the 600 ml bottle because that information is mentioned on the label. The label says that it is 600 ml. So we take the fact that since it is written on the label that it is 600 ml, so we are assuming that what is mentioned on the label is true. But if I want to test whether it is actually true, or if I want to know if it is actually true, is the concept of hypothesis testing. Like I told you earlier, you're given a statement, somebody is telling you something that this happens, but how do you assure whether or not it happens in real? You test it, and that is the whole concept of hypothesis testing. So now, why are we kind of interested in knowing if it is actually true? I'm saying that it is mentioned on the label, I'm assuming it to be true, but why do I want to test if it is true? What difference does it make if I'm trying to test whether or not that claim is true? So the difference it's making is that if you look from the customer side, if you look from the side that I'm going and buying a Coca-Cola bottle, so as a customer, you want that bottle should contain at least 600 ml. Okay, so you're paying say 35 rupees for 600 ml bottle. So if you're a customer, you'll want that there should be at least 600 ml. If it's a little more, you're okay with it, but at least there should be 600 ml. So this is from the customer perspective. The same thing can be tested from a manufacturer perspective as well. As a manufacturer, if you are the Coca-Cola bottle manufacturer, you will want the volume to be exactly 600 ml. Why exactly 600 ml? Because if you're overfilling, if you're filling say 605 to satisfy your customer or to please your customers or to win over your competitor, you're increasing your costs of production. So you don't want to overfill the bottle. Whereas if you kind of underfill the bottle, if you are underfilling the bottle to reduce the cost of production, you upset the customer. So if you see from a customer perspective, you want the volume to be at least 600 ml, whereas if you look from a manufacturer perspective, you want the volume to be exactly 600 ml. So from two perspectives, our hypothesis formulation varies. The truth of being 600 ml from a customer perspective is something different. The truth of being 600 ml from a manufacturer perspective is something different. So for the same problem, when you're trying and formulating the null and hypothesis, null and alternative hypothesis, the statements will vary depending on the side that you're looking from, whether you're looking from the customer perspective or you're looking for the manufacturer perspective. Now, so this is in mathematical terms, as a customer, you'll want the quantity to be 600 greater than or equal to 600 ml, whereas from a manufacturer perspective, you want the quantity to be exactly 600 ml. Okay, so this is this case study I'm going to carry forward through the session today by taking different examples from different hypothesis tests. So continuing this problem, now you want to test whether or not the claim that is made on the label of 600 ml is actually true or not. So what do you do is you take different samples from all over the country. I'm making the assumption that Coca-Cola is consumed throughout a country. So you collect, say, 100 bottles. So it's not viable, it's not feasible to have all the Coca-Cola bottles tested. That is where the concept of inferential statistics will come in. So I'm taking 100 bottles from the entire country. I take some from some state, I take some from some state. Overall I'm taking 100 bottles so that I get a random sample. Now I am taking the volume of each of these bottles to find the mean. So 100 bottles each will have some different quantity, so it's not a perfect place where each of them will have a 600 ml, but there will be some volume fluctuations which I'm going to measure for each of the bottles, each of the 100 bottles that I'm taking. Now when I take the 100 bottles and I measure the quantity that is there in these bottles, I take the mean. So say first bottle has 600 ml, the second one has 602 ml, the third one has 599 ml, and so on. So I take the mean of all that, and then we test the assumption, the quantity that we have measured, we test it against the assumption. This assumption is called as the status quo. So in simple terms, what is mentioned on the label that the volume is 600 ml is the assumption that we are making that yes, the volume is 600 ml. Why is it an assumption? Because we haven't tested it still. But whatever is being claimed, whatever is being assumed is what we call as the status quo. What everyone believes is true is called as the status quo. Okay, now we see two things here. So for a particular instance, let's say the company says that we have discovered some new ingredients. So say the Coca-Cola bottle has a couple of ingredients put in together, and the company claims that they have discovered some new ingredients that they can replace with the old ingredients. Using those ingredients, their production cost reduces. So they are able to sell volumes greater than 600 ml for the same cost. So they put in more ingredients, they put in more volume, but their cost doesn't increase. So for the same cost, they are able to sell more than 600 ml. Now this is the company's claim. Company is making that claim that we are going to sell volumes greater than 600 ml. So the claim that the company is making is not an already existing stuff. Like the company is claiming that it is going to be more than 600 ml, but this has never been tested. Okay, what the claim the company is making has never been tested. So I'm considering two cases. First, when I have the normal bottles and I'm measuring their means. Second is when company has made a particular claim, but I'm not sure whether or not it is true. That has never been tested. So there you see how do we form the hypothesis. So when you're formulating the hypothesis, you need to ask yourself two questions. Okay, so either of these two questions will be true. The first question that you need to ask yourself is if you're testing an assumption or a status quo that already exists, or you're testing a claim or an assumption which is something beyond what you already know. So the first case that we saw where the company is mentioning that it is the Coca-Cola bottle contains 600 ml volume, and it has mentioned that on the label. That is the assumption by which all of us live. We all assume that it is containing 600 ml. So this is a status quo. What is mentioned on the label, what everybody is mentioning, is a status quo. It already exists. So you're testing an assumption or a status quo which already exists. In the second case, the company is claiming that it is going to make new bottles which will reduce the cost, but it will increase the volume to be greater than 600 ml. But this has not been tested. This has never been mentioned on the bottle because the company is yet to manufacture such Coca-Cola bottles. So in this case, you're testing a claim. So this is not an assumption yet because this hasn't happened. The company is only making that claim or that assertion. So in this case, you're testing a claim or an assertion which is beyond something you already know. So out of these two questions, when you're formulating the hypothesis, out of these two questions, one of them will be true. Clear so far? Okay. So after you have asked yourself these two questions and the answer to one of them, the question is yes. So then you come to the concept of null and alternative hypothesis. So the null hypothesis is when something is assumed to be true, or you have a status quo, or something is given to you. For the example of Coca-Cola bottle, when it is given to you that the volume is 600 ml, that is the status quo, and you're assuming that the volume is 600 ml, that is the null hypothesis. So the statement that you make in that case is that everywhere you've anyway accepted, when you're paying 35 rupees to buy that bottle, you have accepted that it is true, that it is actually giving you 600 ml. You've accepted it to be true. Now you want to test it. So this stuff will be called as the null hypothesis. Going to the second case, when the company made the claim of putting in volume greater than 600 ml. So this is the case when company is making a claim that hasn't already happened. Company is making a claim or company is making an assertion, and that is not given to you what the fact is, whether or not the company will be able to make a quantity more than 600 ml is unknown. It's not known yet whether the company will be able to do that or not. That's only a claim that the company is making so far. So that is an alternative hypothesis. So the statement that you make there is that since the company is saying that it is going to do that, so it may be true or it might be not be true, so you're going to test it. Okay, so this is how the null and the alternative hypothesis will vary. If something is assumed to be true, if something is a status quo, or something is given and it has been accepted to be true everywhere, but you still want to test it, so that case it is a null hypothesis. But if something doesn't exist yet, it is just a claim, it doesn't exist yet, somebody is only making a claim that they are going to do something, they haven't done it yet. So with the null hypothesis, they have manufactured bottles, they have put a claim, they have made a statement that it is 600 ml, they've already done it, and then you're testing it. In the second case, they have only made a claim, they haven't done it yet. So that will be the alternative hypothesis. So null hypothesis, you normally represent it by an H sub O, and you call it as H naught. The alternative hypothesis, you write it as H sub A and you call it as HA, which is the alternative hypothesis. So you need to be careful when you're solving any problem. From the problem statement that is given to you, you need to clearly figure out whether it is an assumption, status quo, claim, assertion, what it is, and depending on what it is, you need to formulate your null and alternative hypothesis. Okay, but so whichever you form first, depending on what the problem tells you, what is given in the problem, what is the problem asking you to do, you first form the null or the alternative hypothesis. Once you form the null and the alternative hypothesis, null or the alternative hypothesis, the other will be opposite of it. So if you have formed the null hypothesis that the volume is equal to 600 ml, the alternative would be that the volume is not equal to 600 ml. Going to the other case, if the alternative hypothesis is that the volume is going to be 600 ml, is going to be greater than 600 ml using the new ingredients, the null would be that it would be less than or equals to 600 ml. So anyway, the null and the alternative hypothesis are going to be opposite of each other and they're going to be mutually exclusive. But then which one to form first and which one would be what? So you cannot just put anything random as null hypothesis and the opposite as null hypothesis. You need to be careful in what you put in the null hypothesis and what you put in the alternative hypothesis. Depending on the problem that is given to you, you start off by formulating either of these two. So this is just reiterating all the stuff that we discussed so far. So null hypothesis would be an assumption or a status quo, whereas if this is the null hypothesis where you are testing the assumption or the status quo, and that forms the null hypothesis. So when you reject the null hypothesis, it will be the alternative hypothesis. If you're doing if it's a research question like the second example we saw of volume being greater than 600 ml, that is a research question which you're trying to prove, so that will be the alternative hypothesis. And negation of that research question, like whatever the claim is being made that it is not going to be true, that will be the null hypothesis, the opposite of the alternative hypothesis. One thing to keep in mind is with the symbols, when you mathematically represent the null and the alternative hypothesis, that equality will always be on the null hypothesis side. So something is equal to, something is greater than equal to, or something is less than equal to. So the equality will always be on the null hypothesis side. The alternative hypothesis will not contain the equality. It will be less than something, greater than something, or not equal to something. So this is a way to cross check after you formed your null and alternative hypothesis. You can cross check with these symbols. Now, one more thing to keep in mind when you're writing the statements with respect to the null and alternative hypothesis. So you formulate these statements, you test them using the statistical test. After that, you have to make some inferences. So the inferences you make is you reject the null hypothesis. If that does not hold true, you've done some statistical test and whatever was your null hypothesis, that does not hold true. So if the null hypothesis does not hold true, you say that you have rejected the null hypothesis. Okay, but if what you're testing with the null hypothesis holds true, if you're making a statement that is the null hypothesis and that holds true, so in that case you do not say that you have accepted the null hypothesis. In that case, you're going to say that you fail to reject the null hypothesis. So this terminology is important. If you are rejecting, if you cannot prove what you are mentioning with the null hypothesis, if you're not able to prove it, then say that you have rejected the null hypothesis. But if you're able to prove what you've written with the null hypothesis, then you say that you fail to reject it. Do not say that you're accepting the null hypothesis. Instead, say that you fail to reject the null hypothesis. Okay, and once you reject the null hypothesis, like we saw that they are mutually exclusive events and they're opposite of each other. So when you reject the null hypothesis, you automatically conclude that the alternative hypothesis is supportive. And when you fail to reject the null hypothesis, okay, so why we say that we are failing to reject the null hypothesis is because we so when you say that you're failing to reject the null hypothesis, it does not mean that the null hypothesis is true. All it means is that our assumption or the status quo is being met. It does not mean that whatever you're mentioning has been proved to be true, because we cannot make that statement that whatever we are trying to prove has been has been proved to be true. Hence we do not say that we are accepting it. You'll always say that you're failing to reject it. Okay, so keep this terminology in mind. Do not, so when you do your mini project report submission, whatever the null and the alternative hypothesis you form, keep these statements in mind. Either reject the null hypothesis or say you fail to reject the null hypothesis. And the opposite of that will be the alternative hypothesis. Okay, so let's move on to the example that we were doing so far. So the first assumption that we made that our volume is going to be 600 ml. So since this is an assumption, since it is a claim that our volume is 600 ml, so we are going to consider it as we are going to consider it as null hypothesis. So mu equal to 600 ml. Mu equals to 600 ml is our null hypothesis, and mu not equals to 600 ml is our alternative hypothesis. So reiterating, we took 100 samples from different parts of the country. We calculated the volumes contained in each of those samples, and we took a mean of it. So since this is an assertion or a claim that is being made, that the volume will be 600 ml, so we take it as the null hypothesis, that H naught is mu equals to 600 ml, and the opposite of it would be null hypothesis, that the mean is not equal to 600 ml. Okay, so consider a case 1. So we'll be considering 2 cases here. So the case 1 is that when you test the mean, you test the actual volume in the bottles. So in the first case, after you've done the actual volume measurement, say you get a mean of 600.4. So the mean of volumes in the 100 bottle comes out to be 600.4. So you had mentioned that it is going to be 600 ml. It comes out to be 600.4. In that case, you fail to reject the null hypothesis. Why do you fail to reject the null hypothesis? Is because exactly you're not getting 600 ml. Okay, so our assumption of 600 ml is not exactly coming to be true, but there comes the level of significance, because it is not exactly equals to 600 ml. We were making that claim that it is going to be 600 ml, but it is not exactly 600 ml. So you cannot say that you're proving your null assumption, your null hypothesis to be true. But since it is just slightly more than 600 ml, you also cannot reject the null hypothesis. Hence, you say that you're failing to reject the null hypothesis because you had claimed that it's going to be 600. It is 600.4, which is not exactly the same. It is slightly different. So you just say that you're failing to reject the null hypothesis. Why you're failing to reject? Because there is some level of significance, that there's some level of tolerance that you can allow when you are measuring the sample data. In the second case, say you get a mean of 645 ml. So your claim was that it contains 600 ml, but when you tested it, you got the mean of 645 ml. So in this case, you can clearly reject the null hypothesis, or you can clearly reject the assumption that you had made that the volume is 600 ml. So in this case, you have every statistical evidence to say that the alternative hypothesis is valid because your null hypothesis has been rejected. So repeating it quickly, in the first case, your claim or your assertion was that the mean volume is going to be 600 ml. Because it is not exactly equals to 600 ml, so you cannot say that your null hypothesis has been proved. But you also cannot reject it because there is only the deviation of 0.4, which you know is very likely to happen since you do not have the population data, you just have the sample data. So you cannot prove the null hypothesis, but you also cannot reject the null hypothesis because there is only a slight deviation. So in this case, we say that we are failing to reject the null hypothesis because we are allowing some level of tolerance. In the second case, the mean is very much greater than our assumed or the claimed mean of 600 ml. It's very much greater than that. It's very deviating from that. So in this case, you clearly reject the null hypothesis, or you reject your assumption. And since you're rejecting the null hypothesis and rejecting your assumption, you will say that your alternative hypothesis, that the mean is not equals to 600 ml, holds true. Does all of this make sense? The particular example, why we are rejecting or why we are failing to reject? Why I'm focusing on these why I'm focusing on these a lot? Because these terminologies matter. Rejecting or failing to reject, these matter quite significantly. So I'm putting a lot of focus on these. Okay, so we move on to the type 1 and the type 2 errors. So since you are using samples to infer something about the population, and although you're saying that you're randomly sampling your data, but then you're always likely to make errors. The errors will not be because you're doing something incorrectly. The errors will be because you're using sample to make inferences about the population. So the first kind of error that you can make is you reject the null hypothesis when it should not have been rejected. So if you go to the previous case, you got a mean sample of 645 and you reject the null hypothesis. But say somebody has actually taken the population mean, and in that population mean, that person has got a mean of 602 ml. So that was the population mean, but your sample mean was 645 ml and you rejected your null hypothesis. So there you've made a type 1 error. So you rejected your null hypothesis because you got a mean of 645, but in actuality it should not have been rejected. So you're incorrectly rejecting the null hypothesis and hence you're making a type 1 error. The type 2 error is opposite of it. This is when you should have actually rejected the null hypothesis, but you are failing to reject it. So in the case when you got a mean of 600.4 and you say that I am failing to reject the null hypothesis, say in the population mean the actual mean was 605, wherein in the sample mean you got it to be 600.4. So you said that I am failing to reject the null hypothesis, but in actuality it should have been rejected. So when you're incorrectly not rejecting the null hypothesis, I'm not calling it that you're incorrectly accepting the null hypothesis. I'm saying that you're incorrectly not rejecting the null hypothesis. It should have been rejected in actuality, but you're not rejecting it because of what you got from your stats. You're failing to reject it, so then you commit a type 2 error. So this is the kind of confusion matrix which helps us understand the type 1 and type 2 errors. So if the reality is that you should not have rejected it but you reject it, so that is called a type 1 error, and that is referred to by alpha, the alpha symbol. In a second case, when you should reject it, but when you actually you should have rejected it, but after doing the hypothesis testing you fail to reject it, so this is when you commit a type 2 error and it is represented by beta. In the other two cases, that's a correct rejection or a correct decision, but otherwise you commit a type 1 or a type 2 error. Now there are some reasons on why these errors occur. First is because you're doing a random sampling, so sometime it is possible that you selected a sample which is not representative of the population. So your population mean and your sample mean are varying a lot, varying to a significant amount. So your sample is not actually represented of your population. So even though you're doing the right statistical tests, but your sampling has not been correct, so what your sample says is not actually true about the population. Hence you may commit a type 1 or a type 2 error. So this is in another way of saying that your sampling techniques may be flawed. So you're not actually taking the right sample. So when you say alpha in your questions, in your case studies, when you say alpha, so that is actually the tolerance level that you're giving to your problem to allow making a type 1 error. That is because you know you're taking a sample, so exactly your population mean is not going to be equal to the sample mean. So alpha is the level of tolerance that you're giving to the statistical test to make an error. Okay, so then is the confidence level, which is nothing but what we just saw. So since our alpha was 0.05, which is 30 for 600, so the tolerance level was, the confidence interval was between 570 to 630. That means that when a sample falls between 570 and 630, we are going to say that this is the confidence interval, or we are allowing our mean to be between 570 to 630. This is actually what the confidence interval is. Okay, so when you're working with the problems, when you're working with the case study where it tells you that you have a 95% confidence interval. So 95% confidence interval is equivalent to saying that your alpha is 0.05. So I should have done it as 15 here on either sides. So this should have been 585 to 650. So the total tolerance is 30. So it will be divided by 2 on either of the sides. So it will be 585 to 615. So here when the confidence interval is 95%, that is equivalent to saying that your alpha is 0.05. So if you're considering a two-tailed scenario, in that case the 0.05 will be divided on either of the sides. So you'll have 0.025 tolerance on the left hand side, you have 0.025 tolerance on the right hand side. So you see a blue region that is there, and towards the center and towards the two ends there's a white region. So the line dividing these two regions is called as the critical value. So as long as your value, the value that you're testing, falls in the blue region, you fail to reject the null hypothesis, and if your mean falls in the white region, you reject the null hypothesis. Coming back to this example, our population mean was 600, our alpha was 0.05, which is 30. So in case your sample mean, so I've divided 30 into two parts. So in case your sample mean falls between 585 and 615, that will be in the blue region here. So your critical values here will be critical value 1 will be 585, and critical value towards the right hand side will be 615. So as long as the mean that you're calculating falls in between these two values, you fail to reject the null hypothesis. If the values, the sample means that you're calculating, fall outside of those values, they're lesser than 585 or they're more than 615, in that case you reject the null hypothesis because your values will fall in the white region. Okay, so like I told, alpha is the level of significance or the tolerance level towards making a type 1 error. And same thing if you want to do it for a one-tailed case. So here you allowed that the mean could be lesser or the mean could be greater. In a different case, if the problem cannot afford that it should be lesser than a particular value, all you want it to be greater than a particular value, all the tolerance that you can allow is being greater than a particular value. So in that case, all of the level of significance, which is 0.05, will be on one side. So say you have the population mean again, which is 600. The alpha is 0.05, which is 30, but you cannot, you're doing a one tail test where you cannot allow the lesser side of the values, or you can allow us the significance on the right hand side. So in that case, your sample mean should be between 600 and 630. So then it will be called as a one tail test. So you'll have just one critical value here, which will be 630. So as long as the means that you get are up to 630, you fail to reject the null hypothesis. In case it is more than 630, which is the white region on the right, very right end, that will be when you reject the null hypothesis. Okay, and one more thing to keep in mind here is when you're doing a one tail test, so the alternative hypothesis, so you'll have null hypothesis and you'll have alternative hypothesis. So alternative hypothesis will be on the side where your white region is. So in the graph downwards that you see are white region or a rejection region. So the blue is the acceptance region, the white is the rejection region. So your alternative hypothesis will be on the right hand side. Your alternative hypothesis will be that the mean is greater than a particular value. So wherever is the rejection region, that side only the alternative hypothesis will point. Okay, so moving on with how do you do the hypothesis testing. So this will be, these steps would be helpful for you when you do your case study as well. So follow these steps one by one and you will be able to draw insights from your problem. So the first thing is to be clearly know what your problem is, what the problem is trying to tell you. As the second step, form the null and the alternative hypothesis. For the null and the alternative hypothesis, keep those terms in mind of the figure that I had shown you. If you're making a assertion or you're making a claim or you're testing something that is given, form that as a null hypothesis. Sorry, if you're given if you are given as assumption or you're given a status quo or you're given something, form that as a null hypothesis. But if you're testing something that is being claimed about, if you're testing something which is still unknown to you, form that as a null hypothesis. Whichever you form first, form the other as the opposite of the other. So form the null and the alternative hypothesis. Then you need to determine what test needs to be applied depending on what you're trying to prove or what you're trying to test. We'll see all the different tests in the further slides, but after that determine the test that you want to do. Now you choose the type 1 error. What is the level of tolerance that you can allow your statistical test to make? Choose that. If it is not given in a problem, you assume it to be 0.05. After that, you state the decision rule. So decision rule is nothing but when do you fail to reject the null hypothesis. When you reject or fail to reject the null hypothesis, this is similar to what we saw in the previous slide of the range 585 to 615 or above 630 and all that. So that was actually the decision rule. So which values you get will be rejecting your null hypothesis and which values you get will be failing to reject your null hypothesis. So all of these will be decision rules that you need to state clearly. After that, work on your sample data to calculate the test statistic. So this test statistic will be based on the test that you're doing, the test that you choose in step 3. After that, you calculate the p-value, which is nothing but it dependent on the test statistic. So p-value will only tell you how far the actual value that you've got. So in the decision rule, when you're in step 5, you would have got some critical values. So that will be the borderline in which your values can fall within. So they'll be the borderlines. Then you'll calculate the test statistic in step 7. So the step 8 is nothing but it will tell you how far or how near are your test statistic with respect to your critical values. So if your test statistic is very much very much far or very much close to the values you want, so in that case your p-value will be significant. If they are very close by, your critical values and your test statistic are very close by, in that case they won't be very significant. So p-value is going to tell you the amount of confidence that you can put in your statistical test. After that, using the p-value, you can make inferences about your conclusion. So if your p-value falls around, no, if that depends on the alpha that you're considering. Say for example, you've considered alpha to be 0.05 and your p-value is less than 0.05. If it is significantly lesser than 0.05, so in that case you're very sure that whatever you're saying actually holds true. If your p-value is not significant, so then you cannot be very sure of your results. But your p-value, as long as it is very lesser than 0.05, or if it's lesser, significantly lesser than 0.05, in that case you could be very sure of the results of the inferences or the results that you're trying to prove. So follow these steps when you're testing the hypothesis, be it any type of test that you're doing. Follow these steps one by one and you'll be able to make the inferences. When you consider the type of tests that can be done, you can either have single sample or two sample tests, and within the single sample or two sample test as well, you could have one tailed or two tailed test, depending on how you allow your value to vary. And apart from that, you also have the tests of mean, tests of proportion, or the test of variance. So like you were measuring the mean value in the bottle, you could also be testing the proportion, and you could also be testing the variance. Okay, so starting off with the one-tailed versus a two-tailed test. So consider same case again, wherein the Coca-Cola officials have claimed that the mean volume is 600 ml. So since they've claimed that the mean volume is exactly equals to 600 ml, so you have tolerance level on both the sides. It can be slightly lesser than 600 ml, it can be slightly greater than 600 ml, but you have the tolerance level on both the sides. In this case, it becomes a two-tailed test, and you have critical values on both the sides. In the second case, say the Coca-Cola officials have claimed that the mean volume is greater than 600 ml. So in that case, it becomes a one-tailed test. Why? Because you can allow values only greater than 600. You cannot allow values which are lesser than 600, because the claim that they are making is more than 600 ml. So the lesser than side which you had in the previous in the first graph nullifies here. There's nothing that you can do with the left hand side, so it's only the claim that you have to test whether it is greater than 600 ml or not, and that you can test up to a certain limit. So you can say that as long as it is greater than 620 also, or 630 also, whatever that number comes out to be, you're going to fail to reject the null hypothesis. But according to the claim that is given to you, that it is greater than 600 ml, you this becomes a one-tailed test. One thing to keep in mind here is, since this is a claim being made, the Coca-Cola officials are making this claim or an assertion. So this is an alternative hypothesis. Mu greater than 600 ml is an alternative hypothesis. And if you remember, I told you that the alternative hypothesis will always fall on the side of the rejection region. So here alternative hypothesis is falling on the right hand side, which is also the rejection region. So this is how you distinguish between a two-tailed and a one-tailed test. If you can allow for difference on both the sides, if you can allow fluctuations on both the sides, then it will be a two-tailed test. If you can allow fluctuation just on one side, depending on whether it is towards the left hand side or towards the right hand side, that becomes a one-tailed test. Could be left-tailed or could be right-tailed, but it is a one-tailed test. Okay, so starting off with the different hypothesis tests that we have. So the first test that we have is a single sample Z test, or the Z test. So I told you we have three kinds of tests. One is the test of mean, one is the test of proportion, and one is the test of variance. So Z test is the test of mean. And this is when you are known sigma means that you know what the population mean actually is. So z-test is a very less used test, or it's not very frequently used, because in real life situations you're hardly aware of the population mean. If you're aware of the population mean, then sometimes people say that if you're aware of the population mean, then why do you need to do any testing on the sample mean? So this is a very rarely used the test. It holds true only when you know the population mean, hence we say that the sigma is known to you. But anyway, if you want to do a z-test of mean, then you calculate z as x minus mu upon sigma upon root n. If you remember, this is the same formula that we studied yesterday with the central limit theorem when we were calculating z. So x is the mean that we're trying to test, mu is the sample mean, sigma is the population mean, and n is the number of data points that we have, which is 100 in this case. The p-value in this case would be if the test statistic falls in the rejection region or not. So the test statistic that you're calculating in the step above, does it fall in the rejection region or does it fall in the non-rejection region? So if say you have specified alpha to be 0.05, so the p-value that you calculate, say the p-value comes out to be 0.01 or 0.02. So since it is lesser than the alpha that you're specifying, in that case you will reject the null hypothesis. If it comes out to be greater than 0.05, for example it is 0.07 or it is 0.1, anything greater than 0.05, in that case you fail to reject the null hypothesis. This could be the null hypothesis, and the alternative hypothesis will come from the previous step depending on which tail test you're doing. But if the alpha is significantly, if the p-value is significantly lower than the alpha value, in that case you reject the null hypothesis. So here I've just showed examples of when you're doing a z-test, what your critical values will look like. So when your alpha is 0.10, so typically this is all the possible alpha values which are normally given to you in the questions. Mostly it will be 0.05, but sometimes people also do 0.1 and 0.01. So I've kind of put in the critical values for your reference, which should come when you're doing a two-tail. So the first row shows when you're doing a two-tail test, depending on the alpha values, what your critical values would be, and the second row shows what should be the critical values when you're doing a one-tailed test. So whatever the test statistic that you calculate, if the test statistic falls in the shaded region that you see towards the tails, if your test statistic falls in that region, then you reject the null hypothesis. When you're rejecting the null hypothesis, you also calculate the p-value, and you notice that the p-value will be lesser than 0.05. If your test statistic that you're calculating in the first step comes in the white region or the non-shaded region, in that case you fail to reject the null hypothesis, or you will be accepting the alternative hypothesis. In this case your p-value will be greater than 0.05. Okay, so z-test was the test of mean when your sigma or the population mean is known to you. In normal cases, the population mean will not be known to you, and hence we'll be doing a test of sample. So when the population mean is not known, we do a t-test instead of a z-test. So the formulas remain pretty much the same. There is no change except that the symbol sigma gets replaced by s. So s is nothing but the sample mean. Otherwise, the formula remains the same. X bar minus mu upon sigma changes to s divided by root n. So s is nothing but the sample mean, and it becomes a t-test of mean. Otherwise, all the things will remain the same. P-value will tell you whether or not your test statistic falls in the rejection region. If your p-value is significantly lesser than alpha, in that case you reject the null hypothesis. If it is not less than alpha, then you fail to reject the null hypothesis. So with the z-test, you were using the norm s dist function to calculate the p-value. You'll be using the norm s dist function in Excel to calculate the p-value. Here the change will be just that instead of using the norm as dist function, there's a specific test in Excel for the t-stat, that is the t dot dist function or t dist function depending on the Excel version that you're using. So these will help you get the p-value for your particular problem. So t statistic, if you see, also depends on the sample size. So the z statistic that we were seeing, this was irrespective of the sample size you take, whether you take a sample size of 30 or you take a sample size of 100, these critical values are not going to change. But that is not the case with the statistic. It varies with the sample size. So here, for example, I've taken an alpha value of 0.05 constant and I have a sample size of 30. In that case, my critical values are something else. If I increase my sample size, my critical values change. If I increase the sample size, my critical values come closer. So as I am increasing my sample size, my critical values come closer to the centered mean. So for sample size of 30, they were 2.0 plus minus 2.045. If I increase it to 100, they come to plus minus 1.98. So as you increase the sample size, keeping the alpha same, your t-stat value changes. It will vary depending on the sample size. And this we represent, we don't use directly the sample size when calculating the test statistic. We use a term called as degrees of freedom, which in for a single sample test, the degrees of freedom is nothing but sample size minus 1. So for the first case here, the degrees of freedom will be 30 minus 1, that is 29. And for the second one, it will be 100 minus 1, that is 99. So we call that as a degrees of freedom. So these were the two single sample tests of mean that we did, depending on whether we have the population mean or whether we have the sample mean. We'll be doing a z test or a t test, but these are single sample tests of mean. Next we come to two samples tests of mean. So say going back to the Coca-Cola example, we kind of take two samples from two manufacturing centers, one located in one location, one located in another location, and we take two samples from two manufacturing centers. So when we're doing the hypothesis testing, we'll make an assumption that the mean difference between our two samples will be 0, because we wouldn't want that one of our manufacturer is pouring in more volumes and one of them is pouring lesser volumes. We'll want both of them to pour in 600 ml. So we'll make an assumption that mu1 is, that is the volume by the first manufacturer, mu2 is the mean volume by the second manufacturer, mu1 should be equal to mu2, or the difference between mu1 and mu2 should be 0. That will be our null hypothesis. So in this case, again, when you have two samples, if the population means are known to us, we use the z distribution. If the population means are not known to us, we use the t distribution. The formulas remain the same, just that the symbols will change. Sigma is the population mean, s is the sample mean. So the formulas will remain the same, just that the representation will change depending on whether the population mean is known to us or not. So d naught that you see in the z formula is nothing but the hypothesized mean. So in our example, we are saying that the difference between the two means should be 0. So d naught should be 0 here. If, say, for example, I would have told that I want the difference between the two manufacturers to be 5 ml, then in that case d naught would have become 5. So this is the hypothesized mean, the mean that we want to prove. Here we want to prove that the mean difference between the two should be 0. So we'll put t naught to be 0. Also, one more thing, when you're doing a two sample test, so when you're doing a t-test, so in that case the degrees of freedom, like we saw for one sample, are significant. So one way to calculate the degree of freedom is by this complex formula. So either, sometimes to make things simpler, because you have a t sample test, so people normally do a n1 plus n2 minus 2. So n1 is the first sample size, n2 is the second sample size. So normally people do calculate degrees of freedom as n1 plus n2 minus 2 for a two sample test. But if you want to be very accurate in calculating the degrees of freedom when doing a two sample t-test, so this is the complicated formula which you should be using to calculate the degrees of freedom. Okay, so S here is the standard deviation and N is the sample size. N1 is the sample size of first one, N2 is the sample size of the second sample. So moving on to another version of t-test which we sometimes encounter is, so if you saw two samples here, they were samples taken from two different manufacturing centers. One manufacturer center located in one location, the other manufacturing center located in other location. Sometimes you also do a matched sample or a paired sample test, paired t-test. This is when you, for a particular center itself, you test what was the mean before, and say you do some operation, and what was the mean after. So for example, say that for a particular manufacturing center, some manufacturing issues occurred and the caffeine level that was allowed in the Coca-Cola bottle increased the permissible limit. This happened in one of the manufacturing center. So where you took a sample of 100 bottles, say the average caffeine which was permissible to be 10, I'm making this assumption that it is permissible to be 10 microgram, it came out to be 10.5 microgram. So that these bottles, the manufacturing center was told that these bottles cannot be sold. So what they did was, the technicians there worked, and they derived a technique in which they told, we'll do something with these bottles, that could be any process, we'll do something with these bottles and we'll correct the caffeine level. So this is just random assumption that I'm making, that they derived a technique and they claimed that we'll be able to correct the caffeine levels in the bottle so that we don't have to throw them away. So the 100 sample bottles that you took, they went through this technique, and then your caffeine levels are measured again. So in this case, what happens is, you have 100 samples for which you've measured the caffeine limits and they came out to be a mean of 10.5. You pass them through an operation or a technique and you measure the caffeine level again in those same 100 bottles. So you had 100 bottles in the first place, they went through some operation, and you have those same 100 bottles again. So you do not have 100 bottles from one center and 100 bottles from another center like we saw in the previous example. You have 100 bottles in one manufacturing center undergoing an operation, and the same 100 bottles being tested again as a second sample. So in that case, your t statistic formula changes. So d bar, mu d, and standard deviation. So d bar is the mean difference, mu d is the hypothesized difference that you want, and st is the standard deviation. Let's take this for an example. So say the caffeine levels before were calculated. For the same bottles, the caffeine levels after were calculated. So the difference in the first one was 0.2, the second difference was 0.3, the third difference was minus 0.2, and so on. So when you do a mean of these differences, so 0.2 plus 0.3 minus 0.2 and so on, when you do a mean of all these differences, it comes out to be d bar. Okay, and mu d will be the hypothesized mean, how much you want the mean to decrease here. So here say you want the mean to decrease till 0.5, because the actual value was 10.5 but the permissible is 10, so you want to decrease it by 0.5. So mu d will be 0.5 here, that is your hypothesized mean. And finally the standard deviation, whatever the standard deviation you calculate for the difference. So 0.2, zero point 0.3 minus 0.2 and so on, you have that for all the 100 values. So you will be calculating d bar as the mean of the differences and st as the standard deviation of these differences. So this is little different from a 2 sample or a 1 sample test. Okay, so far we did 5 tests overall. We did 1 sample test of mean z test. We did 1 sample test of mean t test. Then we did 2 sample test of mean z test and 2 sample test of mean t test. Then just now we did the match sample t test. So we've done 5 tests of mean so far. One more kind of test we can do is the test of proportion. So far I was just measuring the mean volume that was available in the bottles. Sometimes you also need to do a test of proportion, and there we do a z test. So test of proportion is nothing but on the volume that we are filling here, or the volume that is considering here. We're not considering the volume or the mean volume contained. We are doing some test of proportion here. Like for example, you have the mean of 600, which you say is a nicely filled bottle, but say in a particular year the Coca-Cola officials noted that 30% of these bottles were underfilled, means they had a volume lesser than 600 ml, and they took some corrective measures. 5 years later they sampled 300 bottles and they determined that 76 of them were still underfilled. Now you want to test whether or not some corrective measures, whether or not you can claim that some corrective measures have been taken or not. So it was noted that 30% of the bottles were underfilled. You took a sample and you took a sample of 300 bottles and 76 of them you found to be underfilled. Now you want to test whether or not some corrective measures have been taken. So how do you do that is this, we are not considering the volume of 600 ml or anything here. We're considering the 30% proportion here. So the claim, what was noted by the Coca-Cola official, what was given to the Coca-Cola officials, that is the null hypothesis here, which is the 30%. So it becomes a proportion of 0.3, and your alternative hypothesis is P naught is less than 0.3, because you want the underfilled proportion, which was 30% in the first place, to reduce to be something lesser than 0.3. In the first place 30% of them were underfilled. You want something, the proportion, to decrease to a certain extent. So your alternative hypothesis would be that it should be less than. So your underfilled proportion should decrease. So your P naught is less than 0.3. Then what you actually note after taking the sample that 76 of them are still underfilled, that is denoted by P hat. So P hat will be 76 upon 300. After that you pitch in these two formulas. So if you have just one sample, you calculate a Z statistic using the P hat and the P naught values. If you have two samples, like you took 300 sample from one center, you took a 300 sample for 300 from the other center, so you will have two proportions, P1 and P naught. But in either of the cases, you compare these P hat, that is the actual underfilled bottles that you've got, against what your proportion initially was, and you get a Z value. After that all the steps remain the same. You get only the way how you calculate the Z statistic changes. After that you calculate a P value, see whether or not it is significant or it is not significant, whether this test statistic falls in the rejection region or it does not fall in the rejection region. All of the steps remain the same, but how you calculate the Z statistic changes. Earlier you were using the mean and the standard deviation of the values to calculate the Z statistic. Here you are using the proportion values to calculate the Z statistic. After the test of proportion and the test of mean, so we saw 5 tests of mean and 1 test of proportion. Um, then there is another test, which is the test of variance. Um, so again, taking that same example, and this is the question which probably you could let me know. So you have 5 bottles from 2 manufacturers, and they are showing the following quantities. You took 5 bottles from manufacturer 1, and they showed the following quantities of 607, 602, 590, 603, and 598 ml. From the manufacturer 2, they showed the following quantities: 602, 597, 600, 603, and 598 ml. So you've taken 5 samples from 2 manufacturers, and these are the volumes that have been calculated for 5 bottles. So if one of the 2 manufacturers' contract should be renewed at the end of the year, which one do you think should be renewed? You have 2 manufacturers, you've taken samples of 5 from both the manufacturers. Which one of them should do you think would be renewed? Can the first one be renewed? Can the second one be renewed? Or the third one should, or both of them, sorry, should be renewed? Okay, so as a second case, the teams want to ensure that the production pattern should remain same equal to same across all the manufacturers. So do you think the manufacturers qualify this constraint? No, because even though their means are approximately the same, or probably they are exactly the same, but the variance the first one has is greater than the variance that the second one has, so their production patterns are not the same. So there are two tests of mean that we saw. One was the Z test and one was the T test, and then there was one test of proportion that we saw, which again was the Z test. Now there is another test of variance. There are 2 tests of variance that we see. The first one is the chi-square test, the second is the F test. So let's kind of see what the chi-square test does. If you remember from the central limit theorem that we saw yesterday, so the central limit theorem says that when you take samples from a normal population, or for that matter, you take samples from any population and you calculate the sample means, that follows a normal distribution. So when you do a sampling distribution of the means, that follows a normal distribution. This was told to us by the central limit theorem. So if you take samples, the same samples that you're taking in the first statement here, if you take the samples of the same size from the normal population, and instead of calculating their means, you calculate their variances. So if instead of calculating the means, you calculate the variances, so those variances do not follow a normal distribution. The distribution that the variances follow is called as the chi-square distribution, and this chi-square distribution is dependent on the degrees of freedom. So if you have a population and you take different samples out of it, you say you see their means, you record the means of the different samples, and you plot those means. They follow a normal distribution. This is what we saw with the central limit theorem. But instead of means, if you decide to plot their variances, they won't be following a normal distribution. They'll be following a chi-square distribution, where the curve is different than what the normal distribution is. So the variances will follow a chi-square distribution, and this is what a chi-square distribution curve looks like. So similar to the t-test that you're doing, the chi-square test also follows the chi-square test is also dependent on the degrees of freedom. So the curves that you see here for the same alpha level of 0.05, if you have the degrees of freedom 5, the curve is the one that is in blue. If you have a degrees of freedom of 10, the curve is the green one. And if you have a degrees of freedom of 15, the curve is the red one. So as you increase the degrees of freedom for the same alpha level, the height of the curve decreases and its width or the area covered by it. So the area will remain the same. The height of that curve decreases and the width increases as you increase the degrees of freedom, keeping the same alpha level. So like the z-test is not dependent on the degrees of freedom, the t-test is dependent on the degrees of freedom, and also the chi-square is dependent on the degrees of freedom. Otherwise, this stuff remains the same. If you're trying to calculate the chi-square test manually, there is some amount of difference that you see when you do the when you compare this with the z-test or a t-test. The difference here is that if alpha is 0.05, and let's go back to the curves that we had earlier. um, okay, so here when you had the alpha level of 0.05, and I'm considering the first graph where I had n equals to 30, so I took 0.05 on both of the sides, 0.05 divided by 2 on both of the sides. So towards the right hand side, how I got the critical value is 1 minus 0.05. So sorry, 1 minus 0.025, that was 0.975. And towards the left hand side, how I got the critical value is 0.025. So from the left hand side, I say that towards the left hand side the value is 0 on the left end. Towards the right hand side, the right end, the value is 1. And as I move from the left hand side to the right hand side of the curve, my values are increasing. So when I have the left tail of that curve, that is the critical value when my alpha is 0.025, and towards the right hand side, the critical value is when my alpha level is 0.975. This is the same thing when you're doing it for a z-test. Towards the left hand side, the alpha will be lower. Towards the right hand side, the alpha will be higher. But now if you do for a chi-square test, this becomes slightly opposite. How it becomes opposite is, towards the right hand side will be the smaller alpha value, towards the left hand side will be the higher alpha value. This is only when you are solving chi-square test by hand. Towards the right hand side you will have the alpha value of 0.025. Towards the left hand side you will have the alpha value of 0.975, which is opposite from what you see in the z-test or the t-test. The good thing here is that Excel automatically, Excel or for that matter any statistical tool, automatically take note of this constraint. So they automatically solve the things for you, and you do not have to do anything opposite or in a different manner. But if you're trying to do chi-square by hand, you need to keep these things in mind. Hence I've deliberately put this curve to show you that it is slightly different from the concept perspective. But if you're doing it in Excel or any other tool, you should keep it much the same way as you do for a z-test or a t-test. So there the tools have made things simple for you so that you don't get confused. But from a concept perspective, know that the alpha values are opposite compared to what they are in the z-test or the t-test. Okay. So what we do in a chi-square test is, we know it is a test of variance, and we compare the population variance with the hypothesized variance. So the X kind of a symbol that you see is called as the chi-square. N is the sample size, S here is the sample variance, and sigma is the population variance. Sorry, sigma square is the population variance, so sigma is the standard deviation. So the chi-square formula considers three things. N is the sample size, so n minus 1 here will be the degrees of freedom. So degree of freedom, and then you take a ratio of the sample variance and the population variance. That gives you a chi-square statistic. After you've calculated the chi-square statistic, all the steps remain the same. You calculate the chi-square statistic, compare that with the critical values, and if it falls in the rejection region, then you reject the null hypothesis. If the test statistic falls in the non-rejection region, then you fail to reject the null hypothesis. All of those steps will remain the same, just that how you calculating the test statistic, the formula will change according to the chi-square statistic. So here also you can kind of do a one-tailed or a two-tailed test. So for the same alpha level, when n equals to 5 or the degrees of freedom is 4, if you're doing a two-sample test, then you'll have maybe just the right-tailed or maybe just the left-tailed, depending on the problem that you're solving. And if you're doing a two-tailed test, that will be the alpha level of 0.05 will be divided on both the sides. And after that, like I told, the process will remain the same. The p-value will tell you whether or not you reject the null hypothesis or your test statistic falls in the rejection region. So with the z-test, we were using the norm.s.dist function or the norm-s-dist function to calculate the p-value. With the t-test, we were using the t.dist function. With the chi-square test, we are using the chi-square.dist function to calculate the p-value. Only so the function remains the same. The starting part of it changes depending on the test you're doing. For z-test, it is the norm s. For t-test, it is t. For chi-square, it is chi-square. Finally, we have F ratio test, which is also a test of variance. So like we had one sample and two sample tests of mean, similarly we have one sample and two sample tests of variance. So chi-square is a one sample test of variance. If you see here, we had just one sample here, n, which was the sample size. With the f-test, we have two samples. So the best thing about f-test is it is the easiest to calculate compared to all the tests you've seen so far. So with the f-test, you take two independent random samples from a population, and if you were taking one sample, you told that they'll be following a chi-square distribution. If you're taking two samples, your sampling distribution, you say, follows an f distribution. So the F statistic is nothing but a comparison between two standard deviations. So you have two samples, one is sample X and one is sample Y. You have the standard deviation or the variance of both these samples, and you can put any of it. Is just a ratio of the two samples, the ratio of the variances of the two samples. So you can put any of them in the numerator or any of them in the denominator to calculate the F statistic. But to make things simpler, what I normally do is I keep the larger sample variance as the numerator and the smaller sample variance as the denominator. So the sample sizes, whatever the sample size 1 may have a larger variance or the sample size 2 may have a larger variance, but whichever has a larger variance, I put it as a numerator. And both of these may have different sample sizes. The first one can have a different sample size, the second one can have a different sample size, so they have their own individual degrees of freedom, but whichever has the larger variance, put that as a numerator to make things simple. How that helps is if you put the higher variance sample as the numerator, so in that case the F test becomes only a right-tailed test. If you put sometimes the higher variance as a numerator or sometimes the higher variance as a denominator, then every time you have to choose whether you make the F test as a left-tailed test or a right-tailed test. But if you try and put the larger sample variance always as the numerator, in that case your F distribution will become just a right-tailed test, where the null hypothesis would be that both the sample variances are the same, and the alternative hypothesis would be that both the sample variances are indifferent, they are not the same. Okay, so the F curve looks somewhat similar to the chi-square curve only, and So this is one particular instance that I've shown you for alpha level of 0.05 when I had degrees of freedom of 24 and 21. So my first sample size was 25, my second sample size was 22. So I've calculated the degrees of freedom accordingly, and 2.054 is the critical value I get. So I'll compare this critical value with the F stat value that I get. If the S statistic value falls in the non-rejection region, which is the non-shaded part of the curve, in that case I fail to reject the null hypothesis. If the F stat value that I calculate is more than 2.054, in that case it falls in the rejection region and I reject the null hypothesis. Apart from that, the calculation of p-value remains the same here. You'll be calculating the p-value using the f dot dist function, which is again similar to the t dot dist or chi-square dot dist function. You'll be calculating the p-value using the f dot dist function. If that p-value is lesser than alpha, which is 0.05, for example, reject the null hypothesis. If it is greater than alpha, then you fail to reject the null hypothesis. Okay, so these are all the possible hypothesis tests that you can do. To quickly do a revision, we either do a test of mean. So the test of mean can be when the population variance is known. In that case, it becomes a z-test, or the test of mean could be when the population variance or the population standard sorry, the population mean. Yeah, so you do two kinds of tests of mean. When the population mean is known to you, in that case population data is known to you, in that case you do a z-test. If in case it is not known to you, you do a t-test. Within the z and the t test also, you can do a one sample test or a two sample test. If you do a two sample yeah, and with if you do a one sample test or a two sample test, in that case you can also do a one tail test or a two tail test. If you do a one tail test, then depending on what your alternative hypothesis is, you need to choose whether it is a right tail test or a left tail test. If it is a right tail test, then your alternative hypothesis will have a greater than symbol. If it is a left tail test, then your alternative hypothesis will have less than symbol. After that, we also saw the z-test of proportion, which is only a z-test because you always have the population proportion that will be given to you. After that, we saw the third types of test, which was the test of variance. So if it is a one sample test, that is called as the chi-square test. If it is a two sample test, we call it as the f-test. So two tests of variance, z and t, one test of proportion that is one test of proportion that is z, and two tests of variance, which is chi-square or the f ratio test. So these are all the hypothesis tests that we do. I also quickly telling you, so far I told you all the functions that are present in Excel on how you can calculate the p-values in the Excel, but in case you want to use R for practice, so for a z-test there is no exact function that has been that exists, but you can always create a function for doing a z-test, because z is nothing but mean minus mu divided by the square root of variance or the standard deviation upon square root of n. So you can just create a function for yourself in a similar manner for a z-test. For a t-test, there is this function of t.test, which is present in probably the base stats package only. So you specify what your data set is. So if you're doing a one sample test, you pass your data set just as x. If you're doing a two sample test, you pass it as y. Then you specify your alternative hypothesis. If it is a two-sided, if it is a two-tail test, then you put it as two-sided. If it is a left tail test, you specify it as less. If it is a right tail test, you specify the alternative as greater. Then you put your confidence level, which is 1 minus alpha. So if your alpha is 0.05, put the confidence level as 0.95. If you're doing a paired test, like we saw a mat sample test in one of the cases, if you're doing a paired test, put paired equals to true, otherwise the default value is paired equals to false, and mu equals to 0 is the mean that you're trying to test. That is the hypothesized mean. So using this function, you can perform the t-test in R. Then for chi-square test, the function that you can use in R is the sigma dot test function. So again, here you pass the data set. You pass what your sigma value is, what your standard deviation value is. Then you give the alternative hypothesis, whether it is a two-tailed, whether it is a one-tailed left or a right-tailed test, and what your confidence interval is. And then for the F test is nothing but you're comparing two variances. So F test is represented by VAR, var dot test, in which you give the X and the Y data sets. What is the ratio between them you want? If you want both the variances to be equal, then you put that as 1 or whatever you want it to be. And similarly, you give the alternative hypothesis, two-sided, one-sided, left or right, and also the confidence interval. So instead of using Excel, if you want to use R, you can use these functions to do the hypothesis tests. Thanks. Have a good evening.